In the next, let us explain the computation process of the convolutional operation on a two-dimensional array. Take for example, we consider a very simple array that is 5 rows by 6 columns, and the convolutional kernel is 3 by 3, which is illustrated in this figure. So the first step in a real computational method implementation, it is to decide what is the size of the output of this operation. Let us consider the convolution operation. As discussed before, we first apply the kernel, the convolutional kernel, at the up left corner of the input two-dimensional array. By applying, we mean to take the element-wise product and take the sum of these 3 by 3 line products. Then this will generate one output, for example here, and in the next step, this kernel is moved by one element. In this case, for example, the array are pixels in an image. That means moved one step, one pixel to the right, and then compute the next output. So on and so forth until we reach the border of the row. When we consider the computation of the convolution, this isn't of much concern at the border. But in practice, if we try to compute one more output, we will find that there will be no valid elements in the input array to take the product with. So it is not very difficult to find that if the width of the input array, for example, is W input, and the kernel size is K, then the output array will have the width of Wi minus K plus 1. So the rightmost position at which we can start the computation is exactly key elements from the right hand side of the input array. Okay, so in this case, 3 by 3 kernel and 5 by 6 input, we will end with 3 by 4 output. Okay. So first, let's just consider this part, this output. We will adopt a slightly different notion as we introduce the computation of the convolutional operation. So the location of the output is specified by, when we consider the computation here, instead of using the central location here, we use the up left corner. So this corresponds to here. Okay, so this element corresponding to applying the convolutional kernel at this area, as we just discussed. So in this part, we just randomly generate a 5 by 3 array and a 3 by 3 kernel. So let us illustrate the computation of the convolution here. Let's see, for the output, we want to compute the ith row and the jth column of the output array. To do that, we need to scan over the area of the kernel. For example, we take the 3 rows and take the 3 columns of the kernel. and let us initialize the sum to be 0. So we increment it by array A and start from the ith location, and offset is the coordinate in the kernel P, and G with offset of Q, and the product is taken to the kernel location, a kernel coordinate P and Q. So that will be the output, the corresponding output element here. This guy. Let's see. Okay, here we have a number. Looks looks reasonable. So to compute for every output, we will need 2 layers of outer loop, which covers all possible outputs here. Therefore, let us consider the output to be that would be 3 by 4. So and then now we consider the corresponding location at B, I, and J. We do not actually need an S here, but anyway, we can make it easier to understand. We initialize a sum 0 and take the pairwise product here, and we can let B, I, and J to be the S. So let's print B to see the result. Okay. So this is the procedure of computing the convolutional kernel.